Good morning, everyone. Today we are going to learn a very important topic in a basic electrical engineering, that is a transformer. You heard this word transformer? Today we will discuss about the transformer. So transformer, why we are going to use this transformer? Before we are going to know the transformer definition, so why we have to study and why we have to read this particular topic in the BEE? So basically we know that the electrical energy is an important source for human life. So it is generated from different sources like water, coal, nuclear fuel, water by using of coal and nuclear fuel. So by using of water, the hydropower, for the using of water, the power is generated, that is a hydraulic power plant. By using of coal, so the power is generated in the thermal power plants. By using of nuclear fuel, so the power is generated in the nuclear power plants. We know that. So these plants are located far away from load consuming centers, that is cities, towns and villages. Is it true? So these plants are basically these thermal power plants, nuclear power plants and hydro power plants are located far away from our load consuming centers. So power is to be transmitted from consider distances. So the electrical energy is generally used at usually, so then generated, that is 3.3 kV, 6.6 kV or 11 kV, like that 33 kV, like that the power is the electrical energy is generated. So in this particular energy is generated from the power plants. So this electrical energy is generally transmitting the electrical energy at these voltages. It's not economical due to the more voltage drops and ohmic losses in the transmission lines. So we have one device, so that device is required for stepping up the voltage at generating station and the stepping down the same voltage at the load consuming centers for utilization point of view. So if we are going to understand easily, so for example, the power is generated in a generating stations. So whatever the power is generated here, so we are going to utilizing in our household and appliances or the domestic purpose or consuming loads. Here we are going to represent it, right? So in this, power is transferred from this place to this place through transmission lines. Through transmission lines, the power is through transmission lines, the power is transferred from the generating stations to the consuming station or consuming load centers. The power is generated, means that is a transferred from the generating stations to the consuming loads. But in these in this particular, the ohmic losses, the voltage drop will be existed. So whatever the requirement of the voltage we occurred in the consuming centers, but we are not getting that the exact value of the supply we are not getting it. So based on that, we are going to represent it basically through the transmission line. These transmission lines, we are going to use one device. That device we are call it as the transformer. Either we are going to represent as a stepping up the voltage or stepping down the voltage. Based on our requirements, so we are going to use this device is a transformer. So it is we are going to represent this is a transformer. Based on that is here I am going to consider as the isolation transformer because the both the primary and secondary windings are same. So it is required based on we are going to represent as a high voltage, that means a step up transformer we require. So the more number of windings are more compared to the primary side. If we are going to represent as the less voltage is required, that means step down, that means the less number of windings are there in the secondary side when compared to the primary side. So now we are going to represent as the basic definition of a transformer. So we know that why we are going to use this transformer, right? So the basic definition of a transformer is a static device. It is a static device which transfers the power from one place to or one circuit to another place or circuit without changing frequency. Without change in frequency. So we know that the basic definition of a transformer is a static device which transfers the power from one place to another place without any change in frequency. So it can raises or lowers the voltages which is corresponding to the decreasing and increasing the currents. So the main advantage of alternating currents over a direct current is that the alternating currents can be easily transferable from low voltage to the high or high voltage to the low. But in this alternating voltages can be raised or lowered as per requirements in the different types of electrical networks as already discussed in the generation, transmission and distribution and the utilization point of view. So this is a possible with a static device, that is a transformer. So the transformer works on the principle of mutual induction. So it transfers an electrical energy from one circuit to other circuit where there is no electrical connections between two circuits. So now coming to this working principle. So already we know that the transformer works on the principle of mutual induction, that is Faraday's laws of electromagnetic induction. So basically the Faraday's laws of electromagnetic induction, we have two laws. That is the Faraday's first law says that whenever a conductor cuts the magnetic flux lines, an EMF will be induced in that conductor. The Faraday's second law says that the magnitude of the induced EMF is directly proportional to the rate of change of the flux linkages. So mainly we are going to represent as the principle of mutual induction states that when two coils are inductively coupled, the two coils are inductively coupled, not in electrically coupled, right? So in this inductively coupled, if the current is one coil is changed uniformly, if one coil is changed uniformly, and EMF gets induced in the other coil. So this EMF can drive a current when a closed path is provided to it. So the transformer works on this same principle. So in an easy way we can understand this concept in an elementary form. So it is consists of a two inductive coils, right? These two are in inductive coils. so which are electrically separated but linked through a common magnetic circuits. So having a high mutual inductance, the two coils are linked by a common magnetic flux, a path of a low reluctance. So these coils are wound on a laminated core of a magnetic material. So whenever we are going to, for example, the current is passing through this coil, the flux is produced in this winding. So that flux is linked with this winding, then the EMF will be induced in the other coil. So then here we are going to represent as it gets the induced EMF, that EMF we are going to as a mutual induced EMF. So based on that principle only that transformer will work. So basically the transformer, the basic transformer we are going to draw this one. So this is the magnetic core, is the magnetic core. In this magnetic core we are going to represent as the windings, right? So here we have two windings, that is the LV or H winding. For example, I am going to represent as this is the LV winding and this is the H winding. So basically here we are going to represent as that it consists of N1 number of turns here. For example, here I am going to represent as N1 number of turns, here N2 number of turns. So when we are call it as the primary and when we are call it as a secondary. So basically here we have two types of winding, that is LV winding and HV winding. So whenever we are going to give the supply, whenever we are going to give the AC supply to one of the winding, whether it is a LV winding or HV winding, that we are call it as a primary winding. That we are call it as a primary winding. Whenever we are going to connect the load, whenever we are connected the load terminal to one of the winding, whether it is a LV winding or HV winding, LV winding or HV winding, that we are call it as a secondary winding. So based on that only we are going to represent as N1 number of turns in a primary side and N2 number of turns in a secondary side. So based on that we are going to represent as in a AC supply, I am going to connect it in the primary side. Whenever we are going to connect at the primary side, that is the AC supply. So the primary voltage will connected to the primary winding, then the primary current will flows. So whenever the current is passing through this winding, then the flux will be produced as according to the Faraday's law. That flux only links with the entire magnetic core. Entire magnetic core. So that flux only links with this secondary winding, then the EMF will be induces. Then the secondary winding is connected to the load terminal. So in that EMF gets induced in that coil, then this current is drives in the secondary winding, then the EMF will be induces in the secondary side, that we are going to represent as a mutual induced EMF. So when we are going to represent as in a primary side, we are connected to the number of turns, that we are call it as a N1 number of turns, and the secondary we are call it as the N2 number of turns. So the graphical representation of a transformer, the graphical representation of a transformer we are going to represent like this. So if we are going to represent, I am going to represent as the more number of turns are less when compared to the secondary side. Now you are observing here. That's what I am going to represent as this is the LV winding, this is the HV winding. So in this I am going to give the supply AC supply. So we are going to give the AC supply, that voltage will give, then the current is passing through this winding. So the already we discussed this is not electrically coupled, this is the magnetic coupled. Whenever current is passing through this winding, the flux will be produced. Based on that flux is linked with the entire magnetic core. Whenever we are connected to the load, then that here EMF will be induced in the secondary side. So here we are going to give the supply V1 and the current is passing through the primary side. The primary of the windings number of turns are we are going to represent as N1. The number of turns in the secondary is N2. Then the EMF will be induces in this, the secondary coil. Again the load current will be produced because we are connected the load in the secondary side. So the terminal voltage is appears crossing this load terminal. So the EMF will be induced in the secondary side. So these two parallel lines represent as the magnetic core. The two parallel lines represent as the magnetic core. This is the graphical representation of the transformer. Otherwise, we can represent as the symbolic representation. Symbolic representation of a transformer. So the coil connected to higher voltage circuit is called as a high voltage winding. Here we are going to connect the low terminal to the secondary winding, that means H winding, that we are call it as a high voltage winding. Other connected to the low voltage circuit, that is a low voltage winding. So when a primary winding is excited by the alternating voltage, it circulates an alternating current. So this current produces an alternating flux, so which completes its path through the common magnetic core. So already we discussed in the previous one only. So whenever we are going to connect this one, the primary side, the supply, so it has a primary winding and it consists of a secondary winding. So whenever the supply we are going to give it, right, the current is passing through this winding. That current, based on that the current is passing through this winding, the flux will be produced. That flux is linked with the entire magnetic core. So this current produces the entire alternating flux which completes its path through the common magnetic core. So this dotted line shows the flux. So thus an alternating flux links with the secondary winding. This alternating flux is linked with the secondary winding. So according to the Faraday's laws of electromagnetic induction, so the mutually induced EMF gets developed in the secondary winding. So here the EMF will be induced in the secondary side. So based on the electromagnetic induction, mm, the load is connected to the secondary winding. The EMF drives a current through it, that is E is equal to the M into di by dt. So basically the E is the induced EMF. So M is the mutual inductance. I is current flowing through a primary winding and T is time taken for the change of the current. So this is the way the transformer will works. So now we have to know. So we know that in a transformer we are going to give the AC supply only. So why can DC supply be? May I know the? May I ask the question? Can DC supply be used for transformers? Is anyone? So here the uh, transformer on DC supply. We know that we are going to give the transformer in AC supply. But here I am going to represent as a transformer on DC supply. What will happen? If the DC supply cannot be used for the transformer. So the transformer works on the principle of mutual induction, for which current is one coil must change in uniformly. We know that. So in DC supply is given, the current will not change due to the constant supply. The transformer will not works. If we are going to give the DC supply, the current will not change, because in a DC supply the current is constant. So the current supply, it's not change in constant supply. So the supply, the transformer will not works. The practically winding resistance is very, the practically the winding resistance is very small. So in a DC, the inductive reactance is XL is equal to 0. So has no frequency. The inductance reactance is 0, then it has no frequency. So total impedance of the winding is very low of DC. So the practically winding resistance is very small. That's what we are not using the DC supply. So then coming to this, the windings will draw very high current if DC supply is given to it. So this may causes the burning of the windings due to extra heat generated and may cause permanent damage to the transformers. So that is the reason we are not going to give the DC supply to the transformer. So now one more uh, disadvantage also there while we are going to give the DC supply. So, so there can be saturation of the core due to which transformers draws a very large current from the supply when connected to the DC supply. So that is the reason the DC supply should not be connected to the transformer. Now coming to the classification of transformer. Coming to the classification of transformer. So based on the phases, so we have two types, that is a single phase transformer and three phase transformer. Based on the phases, we are going to represent as the single phase transformer and three phase transformer. Based on the construction, based on the phases, here we are going to represent based on number of phases, we are going to represent as a single phase transformer and three phase transformer. Based on the construction, based on the construction, consists of three types, that is a core type transformer, shell type transformer, and berry type transformer. We are not using the berry type transformer nowadays. We are going to use only the core type and shell type transformer. So based on the construction point of view, we know that. So based on the function, based on the functions, we are going to represent as the power transformer, that is a step up transformer or step down transformer, so that we are call it as a power transformer. In that step up and step down transformer. And for the distribution transformer, another based on their functions, we are going to represent as a power transformer. And the next one is a distribution transformer. Then we are going to represent as a instrument transformer. Please note down, it is very useful while the classification of transformer, the question will comes. So in that distribution transformer, instrument transformer, in that instrument transformer again it's classified into two types, that is a current transformer, CT, potential transformer, PT. So lastly we are going to represent as based on the function, that we are going to represent as a welding transformers also. Welding transformers. Based on the cooling methods also, it will represent the classification. Based on cooling methods, it classified into two types, that is air cooled transformer, oil cooled transformer, so coming to the based on a location, based on location we are going to represent as the transformer, that is indoor transformer and outdoor transformer. Then based on the frequency, there is a low frequency transformer, high frequency, that is a radio frequency transformer. So based on the ratings also we are going to represent as based on the ratings we are going to represent as three types, that is a low rating transformer, medium rating transformer, then high rating transformer. So based on the purpose of transformer, specially we are going to represent Scott connection transformer, pulse transformers, auto transformer, double star connection transformer, double delta connection transformers. These are the classification of a transformers. So these are all about working principle and types of a transformer. Now we discuss about the construction details of a transformer. Construction details of a transformer. So transformer is very simple in construction. It consists of mainly two parts, that is magnetic core and second one is coils or windings. Mainly two parts, that is windings or coils. So basically this magnetic core so the core material, it comes in the particular construction point of view we are going to represent it. Its construction should be such that the maximum flux is created with minimum magnetization current and minimum core losses. The core of the transformer is either square or rectangular in shape. Core or rectangular in shape. So it is further divided into two types, that is limb and yoke. So limb or leg, here we are going to represent as the two types, that is a limb part and yoke part. So here we are going to limb or legs, limb or legs. So this limb, the vertical portion on which coils are wounded is called limb. So basically in this we are going to connect the windings, right? So this is the vertical portion on which coils are wound is called as a, this is the limb portion, or we are call it as a leg portion. So this So the top and bottom horizontal portions are called as a yoke portion. Top and bottom of the horizontal portions we are called as a yoke part. So in this we are going to represent as core is made up of steel due to its high permeability. So high permeability means it is a property of a material which allows the flux freely to pass through it. That's the reason we are going to use high permeability material. So it causes 100% of the magnetic flux produced by primary to be linked with the secondary. So the transformer grade steel consisting of 3% to 4%. Grade steel. Here we are going to represent as grade steel. So that is a 3% to 4% silicon is used to reduce the core losses. So basically we have losses, that is the core losses and the copper losses. In this core losses and copper losses. So again in this core losses classified into two types, that is eddy current losses and hysteresis losses. So we'll discuss later the based on the losses itself. So the increasing in silicon content, basically the high grade steel we are going to using in the magnetic core. So in that that is a percentage is 3% to 4%. So if is increasing the silicon content, it affects the mechanical properties. That means the steel gets brittle if the silicon content is increased beyond 5%. So it will get brittle. So the cold rolled steel is used to reduce the core losses. Basically the core losses, here we are going to using the material is high grade silicon steel. So that is the percentage of steel is 3 to 4%. So in that we have to reduce the core losses. So as the flux in the core is varying, eddy currents are induced in this core. So whenever the current is passing through these windings, the flux will be produced as the flux in the core is varying. This flux is varying in the core. So the eddy currents also induced in the core. So these eddy current circulates in the core. It gives rise to the losses in the core. So whenever the eddy currents are flowing through the core, then it increases the losses also. So to reduce these losses, the cores are laminated. So basically these cores are laminated. The lamination should be insulated. So the thickness of the lamination should be minimum as possible as 0.3 mm to 0.5 mm to reduce the eddy current losses. So the laminations are overlapped so that to avoid the air gap at the joints. So for generally, so L-shaped or I-shaped laminations are used. So basically here we are going to represent as the L shape and I shape of laminations. So here you observe this is L type. Here we are going to observe this. Sorry, this is I shaped laminations. Here we are gets joints. Here also it gets joints. So here another one we are going to represent as a L shaped. This we are going to represent as L type. So is this here? This is the joints. So these are the generally L-shaped and I-shaped laminations. So the cross section of this limb depends on the type of coils to be used, either circular or rectangular shapes. So these different cross sections of a limbs are practically used in this rectangular. So like this is the rectangular. These are the rectangular shape, different cross sections. Here we are going to represent as a square shape also, we are going to represent it like this. These are the cross sections. So the complete laminated core consists of a number of rectangular laminations parallel placed alternatively one over other so that the joints are staggered. So these joints are staggered to avoid continuous gap and to improve the mechanical strength. So otherwise we can represent as the joints are to avoid the high reluctance at the joints. The alternate layers are stacked differently to eliminate the joints. So this is called the staggering. So the advantages of the staggering in the transformers are to avoid continuous air gap, based on that the flux leaks in the air gaps to avoid the leakage flux. So the reluctance of the magnetic set gets reduced. And one more advantage of while we are going to use the staggerings. So basically this we are going to represent as the joints in a particular point of view core type and shell type transformers. So the continuous air gap reduces the mechanical strength of the core. So the staggering helps to increase the mechanical strength of the core. So this is all about the magnetic core. Already we discussed in the it is made up of a magnetic core, and we are using to the high grade silicon steel. The percentage is 3 to 4%. So now coming to the windings. Now coming to the windings or coils. In the starting itself, we discussed about the transformer consists of two windings, that is LV winding and HV windings, right? So in this, the coils used are wound and the limbs are insulated from each other. So the transformer windings are made up of solid or standard copper or aluminum. So the basic transformer, the two windings wounded the two different limbs. So basically here we are going to represent as this is a magnetic core. In this two different limbs. So this is the one of the limb, the windings are wounded, and this is the another limb, the windings are wounded. That means the two different windings are wounded in the two different limbs. That is a primary on one limb, and well the secondary is on the other limb. So but due to this leakage flux increases which affect the transformer performance badly. So to improve the performance of the transformer, so instead of placing primary on one limb and the secondary on other limb, in generally one half of each winding is wounded on each to reduce the leakage flux. So the position of HV and LV windings with respect to the core is also very important from the point of view of installation. So generally the voltage winding is wounded first on the core, on which the high voltage winding is wounded. So based on that we have to improve the performance of the transformer. So a very common arrangement is the cylindrical concentric coils. So it has a single magnetic circuit. The core is rectangular having two limbs. The windings encircle the core. The coils used are the cylindrical type of. So these cylindrical coils are used in a core type transformer. Basically the cylindrical coils so are used in a core type transformer. So these coils are mechanically strong. So basically these cylindrical coils are mechanically strong, and these are wound in a helical layers. Means spring type. So these different layers are insulated from each other by paper, cloth or mica. So both the coils are placed on both the limbs. So these low voltage winding is placed near to the core from each of insulating it from the core. The high voltage is placed after it. So here we are going to represent as these cylindrical coils. So we have to improve the performance of the transformer. So first of all we have to place the low voltage winding. So before that we are going to represent as the insulation. After that we are going to represent as the low voltage winding. Why? Because we have to connect the in the limb part. First of all we are going to represent as a LV winding. Again we are going to represent as the installation. This we are going to represent as the HV winding. By this way the transformer improves the efficiency. So this is HV winding. So the other type of coils which is very commonly used for the shell type transformer is sandwich coils. So these cylindrical coils, basically in this coils we are going to represent as the cylindrical coils and sandwich coils. In the cylindrical coils are used in a core type transformer, and the sandwich coils are used in a in shell type transformer. So in the primary side we are going to connect it in the cylindrical coil, like first of all we are going to represent LV winding and HV winding. Similar way here we are going to represent insulation, then LV winding, after that insulation, then HV winding. So based on that only we are going to represent the performance of the transformer will improve. In the case of the cylindrical coils, this cylindrical type of coils are used in a core type transformer. Now we are going to represent as the shell type transformer. Shell type transformer. So in this we are going to use, that is the windings are that coils are sandwich coils. So each high voltage portion lies between the two low voltage portions, that is a sandwich the high voltage portions. So we know that that is a sandwich, how we will prepare it, two breads, right, in between whatever the required um, like vegetables, otherwise non-vegetarians they are preferred the non-vegetarian non-veg. So based on that, in the between high voltage, for example here I am going to consider the transformer. So in this we are going to represent as, first of all I am going to represent as a high voltage winding, then we are going to represent as a low voltage windings. That means each high voltage portions lies between the two low voltage portions. That means a sandwich the high voltage portion. So this is the sandwich in the high voltage, it lies between the two low voltage portions. So again it is a high voltage, and here we are going to represent as low voltage. Similar way for the secondary side also we are going to represent as a low voltage, a high voltage. That means lies between the two low voltages in between the high voltages. So based on that only we are going to represent to improve the efficiency of the transformer. So such subdivisions of a windings into small portions reduces the leakage flux. So higher the degree of a subdivision, smaller in is the reactance. So the sandwich coil is whatever we are going to represent in the diagram itself. The top and bottom coils are low voltage coils. All the portions are insulated from each other by the papers. So while we are going to represent as the windings, here we are going to represent as the concentric coils are used in a core type transformer. The sandwich coils are used in a in a shell type transformer. Today I conclude these topics. For understanding the construction working principles of a transformer and everything. So thank you. If you have any doubts, please ask me. Thank you.